labor, location, test material, and then what we want to do is standardize. Standardization is a way to reduce cost, ensure cheap, the repair, and so on. Okay, so there are, when you make a part, you have to worry about tolerances. The tolerance is basically dimensional variation. So typically when you look at a shaft, for example, they will say the shaft is 50 millimeters plus or minus 5 millimeters. Just impossible to make a part which is exactly 50 millimeters. You will see that some shafts would be maybe 55, some would be 49.5, but that plus or minus 5 tells you the maximum variation you can expect from a shaft made by, let's say, a particular machining process or some specific company. Now you could have this, you could also have something like this, plus or minus 10 mm. Clearly, you can see that relatively this is a smaller tolerance because of this 5 mm versus this is a larger tolerance. Okay, what it means is that if you have a part which varies by, say, 10 mm, then you might have a problem when you actually put that part together in a component, because it may actually lead to, for example, a clearance, and so you will not be able to put the part successfully in whatever bigger product you're trying to make. And so it turns out that a smaller tolerance is more expensive. This is more expensive than this one, because it will have to go through more processes to get this kind of tolerance. So one way of understanding this cost based on the tolerance is this plot. Yeah.
So when we're like doing design with these tolerances and like planning on using tolerances, can we just like tell the manufacturer +5?
Yeah.
Instead of +5?
You could also have unilateral tolerance. You could have that, yes. Yeah. This is a bilateral tolerance where you're allowing plus or minus. Yeah, absolutely, you could do that, yeah. So here is a graph which shows the cost as a function of tolerance. Okay, so this is in inches. This is in mm. And this basically tells you the kind of processes involved in making this particular part. Let's just take a shaft. So this is assuming you have a lathe, you do a rough turn, then you do a semi-finished turn, a finished turn, grind, hone. Now, each of these processes what will do is they will actually reduce the material and then give you a better and better finish, right? And better tolerance. So as you increase smaller tolerance, as you add in more processes, you get a better and better product, but you can see that the price actually goes up. It actually goes up kind of almost exponentially. It sort of looks like once you think of finish turning, grinding, and honing, because the reason is because, first of all, you require more equipment to do it. The second thing is you require more time to do it, and all those things cost more money, right? So if possible, you want to just limit yourself to whatever minimum is, rough turns, semi-finished turns. Okay, now one thing which we always want to do, as let's say you're a businessman and you're trying to figure out, you may not even the businessman, you could also be somebody who is a manufacturer, right? Who's trying to make his own parts. You want to figure out at what point you will run into a profit. Like initially there are expenses to machine, grind, procure materials, but some point of time you want to spin out enough number of products so that your venture turns profitable. So this is known as the break-even point. Okay, it could also be something which you are concerned about when you are deciding between two machining processes. Maybe machining process one, you need 50 parts to break even. Another one, you require 100 parts to break even. So that can determine what choice you make in terms of what machining process, or could also be a component to use. So the break-even point is defined, and I'm just quoting from the book, the point measured in cost, time, at which, I'll just put a slash here, cost or time at which two processes have the same return. Okay, and I'll do an example which will illustrate this. So break-even point sometimes is about being profitable or less profitable. But here in this case, it's just figuring out, in this problem, which we'll see, it's figuring out if you have an option to make a particular part using two processes, which of those processes, at what point of time would one process beat the other in terms of in terms of cost. Okay, so here's the problem. Okay, I'm sorry that my course was not available, but this is something which I'll post in the handouts before the class, so you can download it and then use that to fill it up if you want in the class. Okay, so there are two machines, A and B. Okay, that may be used to produce a niche product. A has a setup time of 5 hours. Okay, that's something which you need to maybe put things together so that it's ready to produce a part, and then it works to produce 20 parts per hour at the cost of $20 per hour. Okay, that's how A functions. B, on the other hand, has no setup time. You can immediately start producing parts. You can produce 10 parts per hour at the cost of $60 per hour. Okay, so the question is, what is the break-even point? Okay, so I should probably have said, so the break-even point can be in terms of time and cost. In this case, break-even point, I would say in terms of cost. Okay, you should also have a break-even point in terms of time. Which machine will you use for 10 units and which one for 30 units production? So again, assuming that you want to want it to cost the minimum as possible. Okay, so let's write this down in our own words. Let's take A. So A has a setup. Just use a different. Let's just try this. So A has a setup time of 5 hours. What else do we know? We know that it produces 20 parts per hour at $20 per hour. Okay, and then B, no setup time, and it produces 10 parts per hour at $60 per hour. Okay, so since we're interested in figuring out the break-even point in terms of cost, let's assume C is cost, and we are interested in knowing, since it's hints at the number of units produced, let's call X as the number of parts. So what we'll try to do is we'll establish a relation between cost in terms of the number of parts for machine A and same for machine B, and that will give us an idea of what the break-even point is. You'll have two competing costs, and you'll find the point at which cost of A is equals the cost of B, and that will give us the number of the break-even point. Okay, so let's look at the cost A. Okay, so the cost of A, cost of producing parts with A, there's a 5-hour setup time. It's like a dead time. You can do nothing with those 5 hours. But in 5 hours, you would have produced, well, 5 times, well, you could have produced 20 parts, right? And it would cost you 20 per hour, which means that in 5 hours, the amount of money you would lose because you're just spending this time just waiting for this to set up is 5 times 20, it's 100. So there is a dead cost of $100. The moment you decide you want to go with A, you need to spend, you sort of have $100 upfront cost, which you would have spent using making parts. That's something you need to put in right away. Okay, then on top of that, now let's say once you've set up, you want to start producing the parts. So we want to write something which gives us the cost times the number of parts. So X is the number of parts. Let me just write it this way, X parts. And then I need to multiply this by the cost per part. So the cost per part is going to be, well, we can easily do it this way. That's $20 per hour. Okay, and if you divide that by 20 parts per hour, so the key thing here is that to get the units right, so if you divide dollar per hour divided by part per hour, you get dollar per part, right? This whole thing gives you dollar per part. The R and R cancel, and so when you take dollar per part and you multiply with X parts, you get basically dollars. So this whole thing equates to a dollar amount. So what we have here is 100 plus X. So this is the cost of producing X parts. We can do the same thing for B. We have no setup time, so that's 0. Then we have, let's say, X parts. And now we need to write something which gives us the cost per part. So that would be $60 per hour. So $60 per hour, and we'll divide it by 10 parts per hour. Effectively, we get dollar per parts, and so this comes out to be 6 times X. Okay, so what this is saying is that if you want to produce 5 parts using CA, using machine A, it's going to be 100 plus 5, right? If you want to B, it's going to be 6 times 5, so it's 30. So clearly 30 is cheaper than 105. So as you produce more and more parts, the question is, some point of time, the cost of producing parts by A perhaps becomes equals to the cost of parts B, and you need to find that break-even point. So for the break-even point, what we need to do is we need to equate CA to CB. So we have 100 plus x equals 6x. And so clearly x equals about 100 divided by 5, which is at 20. So at 20 parts, the cost of A equals cost of B. That's we break even. Again, probably a better way of understanding this relation is through a plot. So I'm going to try to make a plot of cost of A as a function of parts made and cost of B as a function of parts made, and probably that will be more illustrative of what that 20 really means. So let's do that next. Then 20, 30, 40. Then make it 50, 100, 150. Okay, let's draw. So we have on the y-axis, we have cost. The x-axis, we have parts. The first relation is 6CA equals 100 plus x, okay, which means that it will start at 100. And if you know, this is actually an equation of a straight line, y equals c plus mx, right? So this has an intercept of 100 on the y-axis, and then the slope of the line is 1. So you need to draw a line approximately, it will look like this, with a slope of 1. Let me fix that. This doesn't look right. So when you put, yeah, so you need to fix it a little bit. Hold on. Because it's not equi-space, it's going to be, I need to fix that slope a little bit. So I need it to pass through 120 when I put x equals, so when I put x equals 20, I need it to pass through 120. Yeah.
Also, to get it a little more accurate,
Yeah.
at x equals 50, it would be at 150.
150, okay. So x equals 50, yeah, 50, I don't have 50 there. So 50, and then we draw a dot here, and then that might be a better way to do it. So we just connect. We need 2 points in order to draw a line, just with red. Okay, now it actually doesn't look right. It should be, it looks like 125. Okay, okay, so let's, this point here, if you put in the formula, you have 120. So this is a slope of 1. It doesn't quite look as 1 because of the way the axes are, okay, but that's 1. And then let's do the other equation, which is CB is 6x. The good thing about this equation, it passes through 0, the origin. So it'll be here. And then we can draw, take another point. Let's say x equals 30. So it'll be 180. That's beyond my compass. So to 10, 20, 30, let's just do 180. Okay, so this is 150, so this will be 200 here. So we need it to pass through, when x equals 30, it should pass through 180. See, 180 is here. Okay, so this slope is 6:1. And so the reason I drew this intentionally is because we know that when x equals 20, this will also be, so x equals 20, 6 times 20 is 120. So both of them pass through this point. This is the break-even point. Okay, so now what's happening is the following. In this region, anything which is less than 120, so 20 parts, you can see that this line is below the y coordinate of this line is less than the y coordinate of the red line. It means that B is cheaper than A. Okay, but when you reach this point, this side, here what happens is exactly the opposite. Here A is cheaper than B. Okay, so that's the inflection point. So now the second question, which asks you to figure out which machine will you use for 10 units, which one you'll use for 30 units, can easily be answered if you look at this plot. So if you want to do 10 items, you choose the more cheaper one. So you'll use, so let's say B for 10 units, use clearly B. So the cost is 6 times 10, which is 60. And for 30 units, okay, 30 units is, it's right here, it's in the green region. We'll use A. So the cost is CA equals 100 plus 30, 130. If you do it anywhere else, which is use A for 10 units, you'll incur a higher price than you would for B. Yeah.
So in this example, we're using just linear equations. Will we be using other kinds of?
I think the homework problem has a curve. I'm forgetting. But yeah, you could have a curve, which makes it slightly harder to do this analysis unless you draw more points. I think, yeah, there's a question in the homework. I forget which it's a curve or not. Okay, let's move on. Okay, the next thing is this thing about stress and strength. This is a distinction which is kind of important in this course. Stress and strength. Okay, they seem to be the same thing. Stress and strength have the same units. It's force per unit area, Newton per meter square. However, when you talk about stress, it's at a particular point in the part or product, while the strength is something which you think about as a whole. So, so this is stress is at a specific point in the body, and then strength is something which is as a whole of the body. So it's force. So by the way, this is also force per unit area. Just correct this. So it's force per unit area. Okay, but at a specific point in the body, but strength has the same units. Force per unit area for the object as a whole. And we'll be revisiting this, but it's important that you keep that distinction in mind. Okay, let's move on to one of the most important concept in design. It's called, you might have heard of it many times, factor of safety. Okay, there's another term called design factor, which you may not have heard so much, but we'll introduce that next. So two things here. One is design factor. We'll abbreviate that as ND. And the one which you might have heard a lot of times would be factor of safety. Okay, now they have the same formula actually. So what's the formula? ND or N have the same formula. It is strength divided by the allowable stress. Okay, so if the strength is abbreviated as S and the allowable strength, assuming that's uniaxial load, is sigma. Of course, that will change depending on the type of loading. We'll come to that a little bit later. You see that ND or N have no units. No units. That's because when you are computing the strength and allowable stress, both of them have the same units. So they have no units. Now, if they are the same thing, if they're the same formula, are they the same value for a product? Turns out no, there's a difference. ND is something which you calculate, it's computed before the design is built. Okay, and N is the factor of safety is computed after it is built. Okay, so what does it really mean? Why would they have different values? The reason why they would have different values for a particular part is because of what we've talked about before, standardization. Okay, so because of standardization, ND need not be equal to N. Okay, now all this thing might seem very strange to you. What I'll do is we'll solve a problem which will illustrate how ND comes out to be different compared to N, and that will probably illustrate why that's true. Okay, so we'll do this problem and then stop. Here is the problem. Okay, a mechanical system requires a shaft. The shaft is subject to a normal stress of 10 newtons, has a strength of 2000 Newton per meter square, a design factor of 2. Find the shaft diameter and the factor of safety. Okay, so remember that design factor is something which I give you when you're designing the particular product or material or the object. So here, in this case, let's see what's given. We are given the force. We're given the strength S. And we're given ND. Okay, so ND is before design is built. Okay, now let's use the formula we know for ND in order to compute what the shaft diameter would be. We will solve for part A. So first thing we do is let's write down the formula for ND. It's S divided by sigma. So ND is 2, S is 2000. sigma is down there. So we have sigma is 1000 Newton per meter squared. Now, this is basically a system where you have a shaft like so, and then it's subjected to a force of 10 newtons. And this shaft has some diameter, d. And so we know that if a shaft is subjected to an axial force like so, the stress, sigma, is force divided by the cross-sectional area. So it's pi d squared divided by 4. So we can use this fact to solve for d. D is 4f divided by pi sigma with a square root sign. Okay, let's sub in the values. The force is 10, pi is 3.14, and sigma is 1000. Okay, so what I get from doing that computation is 112.8 mm. Okay, so now based on the specifications, we have come up with a shaft diameter. We need that shaft diameter in order to get that particular design factor. Okay, so what we do is once we get a number for the diameter, we need to look at a catalog to see if we can get a shaft of diameter 112.8. So what I did was I just give you a table, which is again from the book, which gives you standardized shaft diameters. The first one, this is in inches. You don't have to bother with that. It's because it's in mm. This is decimal inches. Don't worry about that. This is the one we need, millimeters. So we look along this and see if we can find a shaft of diameter 112.8. Okay, so we see here we have 45, 80, 100. So we have 100, we have 120. We don't have 112.8. So we need to choose between 100 and 120. Now, here's the thing. If you choose 100, then your stress, because the stress is inversely proportional to the diameter, see it here. Stress inversely proportional to the diameter. If you decrease the diameter from what is required to 100, your stress will actually go up, which means that you'll no longer meet your factor of design factor. So when given a choice between two diameters, you always have to choose the larger of the two values, larger of 100 and 120. So it's 120. So you need to choose d equals 120 mm because of standardization. So let's go back. So we choose d equals 120 mm, and this is the standard size available in the catalogs. This, you cannot buy a size which is 112.8. So this is going to be our answer to the question, what is the shaft diameter, not 112.8, because you just cannot shop for a 112.8 diameter shaft. Okay, so we've got that part. Yeah, question. Yeah.
Back to
Yeah.
the notes on the table. Yeah, I wanted to make sure that I got it. Thank you.
Yeah. So if you go back here, it's 120 mm is stuck with. Now that we have D, let's compute the factor of safety. It's S divided by sigma. S is I think 2000 pi d square. So that's 0.12 converted to meters square divided by 4. And if you crunch in the numbers, you get 2.26. So we have the factor of safety is 2.26. And note that the factor of safety n is not equal to nd because of standardization. So hopefully that's now clear why those two terms are not the same. Okay, so we are out of time. We'll stop and we'll meet on Thursday. Yeah.
Or sigma wouldn't have to be the force over the area instead of just the area.
Oh yeah, I think I forgot something. It's force over the area. My bad. It should be 10 divided by pi 0.12 square divided by 4. Thanks for catching that.